beautiful introduction to a demonstration on how to find the area between two curves using calculus and Riemann sums. Alright, so what we are going to begin with here is an example where we have two curves. We have two quadratic functions going on here. So the top curve is 5 minus x squared. That represents this curve right here. And then we have a second curve, which is the quadratic x squared minus 3, which represents this curve right here. So one thing that you want to notice is we're going to find the area that's shaded in green here. You want to notice that this curve here that I've shaded in yellow is always above the curve that I shaded in blue. So that's kind of an important thing. So when you're doing the Riemann sum, let me just draw a rectangle to kind of give you the idea of what's going on here. In a Riemann sum, we know that we are summing up rectangles really from this intersection point to that intersection point like there. Now, in this particular diagram, this right here represents the base of that rectangle. And this right here is going to represent the height of that rectangle. So we're going to represent this in calculus like this. Okay, so the idea, and I'm going to draw one more rectangle here, just at the side here. What happens is this is dx. Okay, so the base is dx. And then the height of this rectangle is going to be the difference between the y values of those 2 points right there. So what you're doing is you're subtracting the function values. So the curve on top is f of x. The curve on the bottom is g of x. So that's how you're getting the height of that rectangle. Okay, and you have to do it in that order because if you didn't, you would have negative numbers. So this number here is a larger numeric value than that number there. Okay, so that's how we would set up the integral. The first thing that we need to do, though, is we need to be sure that we figure out these intersection points. So I'm going to erase this stuff that I've got on here so you can see this a little bit more clearly. So we're going to find this intersection point, and we're going to find that intersection point. It's pretty apparent from the diagram what it is, but I'm going to go ahead and do that at the side. Okay, so what we have is we have two functions. We have f of x equals 5 minus x squared, and we have the second one, g of x equals x squared minus 3. So you're really just doing a substitution method, and you're basically substituting one in for the other. So you could think of this as, if you want to think of these as y values, which of course is what they are, then realistically what you're doing is you're taking this thing and you're plugging it in for that. Okay, that's why you're setting the functions equal to each other. So you have 5 minus x squared equals x squared minus 3. And we can solve this in a variety of ways. What I'm going to do is I'm going to just add x squared to both sides to begin with. And then that'll cancel that out. And that will leave 5 equals 2x squared minus 3. Okay, then I'm going to add 3 to both sides because I want to isolate the x squared. So that's going to give 8 equals 2x squared. Okay, then I can divide by 2. And then that will finally leave me with 4 equals x squared. Then I can do the square root of both sides. So that will leave me with x is equal to plus or minus 2. And that's what matters, is what the x values are. So what I'm going to have here is I'm going to have this one is negative 2, as is apparent from the diagram, and that's 2 there. Now you don't really have to know what those y values are there, because that's not really important in the integral. So when we set up our integral, we're going to integrate from left to right from negative 2 to 2. And then we're doing base times height again. So the base and the height are represented here. Okay, so the height of that rectangle is given as f of x minus g of x. And then that width is given as dx, like that. So then what I would do specifically is the integral that we're going to work with is going to be the integral from negative 2 to 2. F of x is 5 minus x squared. g of x is x squared minus 3 times dx. Okay, so that's what we're going to work with, is that integral. Okay, so that's the setup. Now I'm going to focus on doing the integration here. Okay, so I'm going to erase some of the things I have here so we can clearly display what's going on. And we're going to go ahead now and we're going to focus on evaluating this this definite integral. Okay, so let's do this over here then. So the first thing I'm going to do is I'm going to just simplify this expression. So I have 5 minus x squared plus 3 dx. So that's going to be the integral from negative 2 to 2 of negative 2x squared plus 8 dx. Now you could go ahead and integrate it right now if you'd like. What I like to do is if I see a common factor, so you're going to notice I have a common factor of 2 that I can take out. In fact, I'm going to go ahead and take a common factor of negative 2 out. So I have negative 2 times x squared minus 4 times dx. And be careful when you factor something. You're doing a pretty long problem, so it makes sense to check every move you do. Just in your mind, do a distributive property and check that. Okay, now what we know is we have a constant. So see, this constant can come out of the integration. So we would end up having the integral from negative 2 to 2 with the negative 2 in front, x squared minus 4 times dx like that. Okay, now we're ready to integrate and evaluate that definite integral then. Okay, so if you kind of think about this, technically what you're doing is you're doing the integral of x squared dx minus the integral of 4 dx. So it kind of goes like this. We know by power rule, this is a power rule integral, so you add 1 to the exponent and then divide by the result. And here, if you have a constant, then you just tack on the x. Okay, if you do a derivative of this, notice you would have 3x squared over 3 minus 4, so it would take you back to where you began. Okay, so again, develop the habit of checking and verifying your steps as you go. Okay, so now what we're going to do is we're now ready to evaluate this. So we have negative 2. We have our antiderivative right there, so that's x to the third over 3 minus 4x, and we are going to evaluate that from negative 2 to 2. Okay, so let's go ahead and do that. I'm going to write this as negative 2. I'm going to kind of have a big bracket here, and then we are evaluating the upper limit and the lower limit and then subtracting the result from the fundamental theorem of calculus. So we're going to do something cubed over 3 minus 4 times something cubed over 3 minus 4 times something. That's kind of building the framework is what I try to get students to do. So you evaluate plugging in the 2, then you evaluate plugging in the negative 2, and then you've got the arithmetic problem that you need to work out. Okay, so now what we're going to do is we have negative 2. We have 8 thirds minus 8 for that piece, minus negative 8 thirds plus 8, like that. Okay, now I'm going to just kind of simplify this. So we have 8 thirds minus 8 plus 8 thirds minus 8. Okay, then combine the like terms. We have 16 thirds there, and then minus 16 there. And then I can go ahead and do a distributive property is what I'm going to do. Okay, so I can put that over 1. I'm doing negative 2 over 1 times 16 thirds. And then I'm doing 2 negatives, so that's going to be plus 32. So that will be negative 32 thirds plus 32. I can get a common denominator by multiplying by 3 over 3. So that's going to leave me with negative 32 plus 96 over 3, and that final answer is going to be 64 over 3. So that's going to be the area under the curve. Okay, so there's a lot of arithmetic going on that, so we have got the precise answer to that problem then. Okay, so this is the integral that ultimately we were working with that integral, and we got that result. Now, a couple of things I want to show you is, you do a lot of work on these problems, so you can take technological approaches to tell if you've got the correct answer. So I'm going to show you a couple of ways to do this. Just with a TI, one thing you can do is you can graph, and I'm not going to, when I use TI, I'm not going to do this graph, the original graph. I'm just going to check this integral. So I'm going to put this function in my calculator. This is what we ultimately integrated, was 5 minus x squared minus 3. And then I can set up a window. We're integrating from -2 to 2. A general good idea is to, go a little below and a little bit above, because sometimes if you're dealing with integrating to irrational numbers like square root of 2 or pi, sometimes the calculator doesn't do this right. So that's what I like to do. So I'm going to use this window. And I could also go -2 to 2 on this one. I'm just going to do that. 0 to 10. And then this will graph the function that we're integrating. Okay, not this, so don't be confused by that. And then we go second trace, option 7, put in the lower limit of the integral, which is -2, put in the upper limit of the integral. It'll shade it, and then it'll give you a decimal approximation. Okay, so what that's doing is it's giving the decimal approximation of 21.3, and those 3's appear to repeat like that. So if you want to see if you're right on this problem, then just take 64 divided by 3, your exact answer, and see if that's 21.3. All right, let's do a drum roll. Are we right? Look at that. We are correct. Okay, so we numerically showed that this is the same. Okay, that's one approach. Another approach I wanted to show you is on the internet, on Geogebra, this website, which is a great website to go to. You can check and verify numerically this way too. Now what I did on this, excuse me, is the upper curve was 5 minus x squared, so I entered that. I entered the lower curve, x squared minus 3. And see, on Geogebra, you can adjust the limits of integration. So we're supposed to go from -2 to 2. See, I'm off a little bit there, so you can do that. And then it gives this approximation right here, 21.33. So you can also use some nice approaches that are on the internet. Geogebra is one of my favorite sites, and then that will verify also, kind of show you the picture, and it will verify it numerically. Okay? All right, so that will take care of example 1. I'm going to go on to example 5. The next one I'm going to look at is example 6. And this one you have 2 trigonometric functions. Okay, so with this one, we're going to be finding this area under the curve bound by 2 functions. So the sine wave is the black curve right there. The cosine curve is the one that's represented in red. And we're going to integrate from these 2 points right here. Okay, first of all, you know this point is 0, 0. The reason you know that is because the sine of 0 radians is equal to 0, so you get that point. Okay, you also know this point, although it's given here, is pi over 2, 0. The reason you know that is because the cosine of pi over 2 is equal to 0, okay, from the unit circle. Okay, now what we need to do is we're going to need to find this intersection point right here. It's pretty apparent what it is, but you want to use your knowledge of the unit circle to figure that out. We're going to have to break this up actually into 2 integrals, and this is real important to understand, is because in this region here, notice the sine wave is above the x-axis, and then it changes, and then from this point to this point the cosine is on top. So we have 2 regions. So I'm going to call this region 1, and I'm going to call that region 2, and I'm going to integrate those 2 regions. Okay, so the first step is let's go through how you find this intersection point. You don't want to go by looks. You want to go through and actually work this out using a trig equation. Okay, so there's two ways to approach this. I pulled up a unit circle on this. You're looking at basically this, and I'm going to actually show you how to solve the equation too. So we have y equals sine x, and then we have y equals cosine x. Okay, so what we're doing is we're trying to figure out where they're equal. So again, you could take the sine x and just plug it in. So you would be solving the equation sine x equals cosine x. You really don't have to solve an equation because the unit circle tells you this. So if you look at the unit circle right here, you want to remember that the cosine is the x value and the sine is the y value, so they're equal at pi over 4. So that right there tells you that that x value there is pi over 4, and the value of that function is going to be square root of 2 over 2. So that's what that intersection point is then. Okay, so that's one way to do that, is just pull up a unit circle and determine that. The other way is to solve this equation. So I'm going to go ahead and solve this equation. And if you solve an equation like this, you've got to use identities, and you actually have to kind of do this first to introduce identities, is you have to square both sides of the equation. So you're going to have sine squared x is equal to cosine squared x like that. Now you have an identity, of course, the fundamental Pythagorean identity is sine squared plus cosine squared x equals 1. And you can solve for either value. What I'm going to do is just move the sign over here to get cosine squared x equals 1 minus sine squared x. And then what I'm going to do is I'm going to replace this cosine with what it's equal to. That way we have one trigonometric function in our equation. So moving on, I've got sine squared x equals 1 minus sine squared x. Now I'm going to solve that equation. So I'm going to just isolate. I'm just going to move the sign here to get sine squared x plus sine squared x equals 1. So that's going to give 2 sine squared x equals 1. Then I can divide by 2 to get sine squared x is equal to 1/2. Okay, then I can do a square root. You got to remember to have the plus or minus there. So I'd end up having sine of x is equal to plus or minus square root of 1 over 2. And that's really plus or minus 1 over square root of 2. And if you rationalize that denominator, you're going to get square root of 2 over 2 plus or minus. Now we're interested only from 0 to pi over 2. Okay, we're only interested in that region. So in other words, we're only interested in quadrant 1. Okay, so what happens on that is you would end up having this point right here. So basically the sine of x is equal to positive square root of 2 over 2 at pi over 4. So that would be two approaches to figuring out that intersection point. I wanted to review how you do that trig equation also. Okay, all right, so I'm going to erase this so we can focus now on the calculus. Okay, so now we're ready to think about our calculus and get everything set up and integrated then. Okay, so we have to do two regions. The area of region 1, we need to set up the integral. So the integral on this one, we're going to integrate from 0 to pi over 4. Again, we're going left to right. We're summing up rectangles from left to right. So the integral is going to go from 0 to pi over 4. The upper curve is sine x. The lower curve is actually just y equals 0. It's the x-axis. So I'm going to put the 0 there really just for emphasis. So we're going to work that out. Okay. Then the area of region 2, what we're doing on region 2 is we're going to integrate from pi over 4 to pi over 2. So again, we're starting here and integrating over from there to there. So we're going to set up an integral this time that's going to go from pi over 4 to pi over 2. And then this time in region 2, the curve that's on top is the cosine. And the curve that's on bottom is y equals 0 times dx. So that's what we're going to have, and then the strategy, of course, is going to be that the total area is just going to be the sum of these two regions. So we need to just go through and work out those two integrals and then go through and add the two things together. So what I'm going to do is just work these out separately, and then at the end I'm going to add those together. So let's start with the first integral. Let's work on the integral from 0 to pi over 4 of sine x dx. Okay? So the first thing you got to know is the integral of the sine is a negative cosine x, and then we're going to integrate that from 0 to pi over 4. Okay? Again, you've done an integral, you're doing a pretty long problem, check your antiderivative. So I'm just going to do this and then quickly erase this. If you did the derivative of negative cosine, okay, remember that the derivative of cosine is negative sine, then those two negatives would make a positive, so then you would be back to where you started. Okay, so at least in your mind or on scratch paper, make sure you did it right. You don't want to proceed through the problem unless you've made sure that that's right. Okay, then what I'm going to do is we're going to go ahead and evaluate this indefinite integral. So I'm just going to take that negative and put it outside, and then when I evaluate this using fundamental theorem, I'm going to have cosine pi over 4 minus cosine 0, and then I can work that out. Now you can refer to the unit circle, so if we look at the cosine of pi over 4, okay, we're looking at the x value. If we're looking at the cosine of 0, we're looking at the x value there. So what I'm going to have when I move this over here is I'm going to have negative square root of 2 over 2 minus 1. So that's going to be written as negative square root of 2 plus 1. Okay, then I'm just going to circle that because that's what the area of region 1 is. So that area is negative root 2 over 2 plus 1. Okay, now what we're going to do is, okay, we've completed that area. So now we're going to move on to the second integral, area of region 2. So we're going to be doing the integral this time from pi over 4 to pi over 2 of the cosine of x dx. Okay, so the antiderivative of the cosine is the sine of x. Okay, remember the derivative of the sine is the cosine. And then we're going to evaluate this from pi over 4 to pi over 2. So using fundamental theorem, we're just going to have sine of pi over 2 minus sine of pi over 4. Okay, then we can go to the unit circle on this one. Okay, so the sine of pi over 2 is the y value, so that's 1. And then the sine of pi over 4 is the y value at pi over 4, so that's square root of 2 over 2. Okay, so that would be the value of that region then. So this region 2 is 1 minus root 2 over 2. Now notice these two things are the same. Okay, so that meant that those two areas were equal. They have a symmetry to them. So now what we're going to do is put this all together. So the total area is going to be the area of region 1 plus the area of region 2. And I'm going to write this as negative root 2 over 2 plus 1. And then this other region was 1 minus root 2 over 2. So we have 1 plus 1 is 2. These are like radicals, so that's negative 2 root 2 over 2. The 2's divide out to give you a final answer of 2 minus square root of 2. Okay, so that should be the final area on that. Okay, and then we're going to go through and we're going to do a verification on this with the calculator real quick as well. Okay, now using my TI on this for checking purposes, now I have to do two integrals. So let me just kind of move this calculator over to the left here. So really what I need to do is I need to verify the areas represented by these two integrals. So we're going to do, we're going to first of all check this integral, and then we're going to check this integral right here, and we're going to see if we get those two answers like that. Okay, so what I'm going to do is I'm going to put in y equals sine x. So I need to get that done. Put in y, clear this out. I'm going to put in sine x like this. Set my window up. We're integrating from 0 to pi over 4, so I'm going to start at 0. And instead of going to pi over 4, I'm going to go out a little bigger because sometimes you'll have some issues with this not working. So I'm going to expand that a little bit. And since I'm taking that to pi over 2, I could scale that to pi over 4. Doesn't really matter what you scale it to. Okay, so let's see. Let me make sure I got that right. So the x max I meant to go from to pi over 2. Okay, now that's pi over 4. And, okay, you can really just go 0 to 1. Scale like that, and then we can graph that. You do want to make sure, of course, you're in radian mode. And then you go ahead and graph that. And then we're going to integrate from 0 to pi over 4. So if I go through and go second trace, option 7, lower limit is 0, upper limit is pi over 4. Pi over 4 is an irrational number, so it should shade it in, and it should give a decimal approximation, which is about 0.92 like that. All right. Okay, so we got about, this region right here was giving about, looks like about 0.29289. Okay. And then you would do the same thing for the second one. You could go through and do the integral of cosine. So I'm going to change this to integral of cosine. Again, it's not a bad idea to expand that window a little bit. It doesn't matter what you put in there. Just go a little bit bigger than 1. You can go to 2 if you want to. And then just graph that out, because all you're doing is checking anyway. Now let's integrate this from pi over 4 to pi over 2. And see if you get the same thing. So I'm going to go option 7. Lower limit is pi over 4. Upper limit is pi over 2. And let's get that worked out. So that area is the same thing. Okay, so I'm going to record that as, that second area was also 0.2928, whoops, same thing, 0.29289. Now we're ready to go through and check and verify that we have the right answer. So what I'm going to do is two things. Okay, first of all, I'm going to add these areas together. 0.29289. Oops, I didn't do that right. 0.29289 times 2. It's going to give that. Okay, now let's take our final answer, which is 2 minus 2 root 2. And let's see if they're the same. Okay. All right. Let's do a drum roll. See if they're right. Okay. Look at that. They're the same. Okay. So that verifies that that's the answer of the problem. So that's how you use your TI on that. Okay. Now I'm going to go to this Geogebra website and just show this a couple of more times. So what we were doing was we had two things. So we had a cosine. So I'm just going to wipe that out, and we had a cosine curve. Okay, we also had a sine curve. So I'm going to enter that. Okay, and let's see, the integral on this one, let's see, I can kind of zoom on this a little bit. We were only looking from, I think, 0 to pi over 4 was what we were interested in. So I'm going to move that over to 0. Then I'm going to move this over to about, let's see, pi over 2. Unfortunately, they're doing decimals on this, kind of like this. Okay, so this may not work real well on this one. So anyway, if you do pi over 2 on a calculator, you're about 1.57. So you could just kind of get a fairly good estimate on this one. And if you did that, it's estimating that area. If we're going like this, it's doing two different integrals. So you can utilize that. If you get this thing put pretty well, you should be able to estimate on this website also. Yeah, now I was kind of looking at this what you have to do on this one, it looks like, I did the sine minus 0 to verify that integral. This website doesn't seem to work quite as good on the trig functions. So you could go through and do a similar thing, just checking each individual integral, and then it should work out okay. All right, so let's move on to the next example here. And this one's got a lot of work in it, so we're going to be looking at the region, the area between these two curves. So what we have on this one is, first of all, this upper curve that is shaded in black. That is the sine of 2x. And then the one that is shaded in red that I'm kind of tracing over is that right there. So those are the two curves. So we do have two regions that we have to do. In this region right here, I'll call that region 1, the sine of 2x is on top of the sine of x. Okay, and then this region here, it changes, so the sine of x is the curve that's on top of sine of 2x for every point in that region. So we're going to go ahead and set up our two integrals. The first thing we need to do with this one is, we got to find intersection points. So we need to find this intersection point right here, this intersection point, and that intersection point right there. So that's what we need to do to start with, is get that done. Okay, so these are solved for y, so we have y equals sine of x, and we have the second function y equals sine of 2x. So it's a substitution method. This plugs in for y, and we're going to solve the equation sine of x is equal to sine of 2x. Okay, now when we do this, what we want to do is, you probably want to use an identity. Okay, so one thing that you would have learned on this, and I don't know why I put that 2 there, that doesn't need to be there. Okay, so what we need to do is use the identity. So one thing that you would have learned is the sine of 2x is the same as the 2 sine of x cosine x. Okay, that's an identity that you can use on that one then. Okay, so I'm going to move this to the other side to get 0 equals 2 sine x cosine x minus sine x, and then I can solve this equation by factoring. So you can factor a sine out of that. So that's going to give sine x times 2 cosine x minus 1. And then you can set each factor equal to 0. So you have two factors. You have sine x and you have 2 cosine x minus 1. So we're going to solve the equation sine x equals 0. And we're going to solve the equation 2 cosine x minus 1 equals 0 as well. Okay, so this one we can solve, isolate the cosine. You can do that in your head. You get cosine of x equals 1/2. So what we need to do is we need to focus on solving that equation and solving that equation. And we're only interested from 0 to pi. So we're solving this equation on the interval 0 to pi. Okay. All right, now it's pretty apparent what some of those intersection points, it's less apparent what this one is, so let's go ahead and do that then. Okay, like magic, a unit circle appears just for reference. Okay, so if you want to figure out where the sine of x is 0, okay, well, one place is going to be there. Okay, so the sine of x is equal to 0 at x equals 0. And then that means that's going to represent this intersection point right here. So that's 0, 0. Cosine of x is equal to 1/2. Okay, it's going to occur there at pi over 3. The other place that the cosine of x is going to be equal to 1/2, and you're not going to find any other place on that interval, but you are going to find this happening. So the sine of x is equal to 0 also there at pi. All right, so what we're going to have is our solutions are going to be sine of x equals 0 at 0 and pi, and then the cosine of x is equal to 1/2 at pi over 3. So that gives you your intersection points then. Okay, so I'm going to just sketch in this intersection point right here is going to be the intersection point. Let me move this up a little bit here. is going to be pi over 3. It doesn't really matter what that y value is. And then this intersection point right here is going to be pi 0. Okay, so that's what we did, is by solving the trig equation, we've got those intersection points then. Okay, so that's stage 1, is to be sure that you can effectively do those things then. Okay, all right, so I'm just going to wipe out the unit circle. Okay, then we're going to be ready to go through and start our calculus and setting up our integrals like that. Okay, okay, so what I'm going to do is I'm going to, just so I have a little bit more room to represent this, I'm going to go ahead and erase what I've done here. And then we're going to set up the integrals and work out the integrals. Okay, all right, so let's do the area of region 1. Okay, so when we set up that integral, we're going to be integrating from 0 to pi over 3, so we're moving from left to right, like that. So we'll set up the limits of integration from 0 to pi over 3. Okay, the curve that's on top is this one, which is sine of 2x, minus the curve that's on the bottom is the sine of x, times dx. So that's what we're going to work with on that. And then the area of region 2 is going to be represented by the definite integral. We're going to go this time from pi over 3 to pi. Again, we're integrating, summing rectangles from left to right. So we want to go pi over 3 to pi. And then this time the things go backwards. The curve on top is the sine of x. And the curve that's on the bottom is the sine of 2x times dx, like that. Now notice the antiderivatives on these two things are just going to be opposite of each other because they're subtracted backwards. So you can take advantage of that when you put this together. And then the total area of this region is just going to be the sum of these two regions that are found from those definite integrals. Okay, so the first thing I'm going to do is I'm going to just work out an antiderivative. Okay, both of these things are going to be similar to each other, so we can go through and work out those two integrals, and we can see what we get then. Okay, so what I'm going to do is you can do this. We're going to work on the integral of the sine of 2x minus the sine of x. Okay, and you can break that up into the integral of sine 2x minus the integral of sine x dx. Okay, I need to put that dx there. Okay, all right, this one requires u substitution. So what I'm going to do is I'm going to let u be 2x. Okay, that means that du is equal to 2 dx. Okay, so that, and what we want is we want dx to just be equal to du. So what we're going to do on this is I'm going to divide by 2. So I get the substitution I can use is 1/2 du is equal to dx. Okay, so I can do that u substitution then. So what I'm working on then is I'm going to work on this integral first of all. So we're going to be looking at the integral of sine of u, since we let u be 2x. Dx is equal to 1/2 du. So if we have 1/2 du, we can move the 1/2 in front of the integral like that, and then we're able to do this integration like that. Okay, so what this integral is going to be is this integral will be 1/2. The integral of the sine is negative cosine of u. Okay, so we'll have that. Okay, then what I can go through and do is, of course, the second integral right here, this integral right here is just going to be the sine of the negative cosine x, like that. So I'm going to go ahead and write this as negative 1/2 cosine. Then I can substitute back in the u value right there to get negative cosine of 2x, and then the integral of the sine x is going to be negative cosine x. So that antiderivative is negative 1/2 cosine 2x plus cosine x, like that. Okay, so we got our antiderivative, and I always say it's important to just double check this. So if you did the derivative of this function right here, let's just check this. You would have negative 1/2. Derivative of the cosine is negative sine of 2x, and by chain rule, the derivative of what's inside is 2. The derivative of the cosine is negative sine x, so you'll have these cancellations, so you'll have a negative negative or a positive sine 2x, so that checks, and then you have a minus sine x. Okay, so those are pretty important things to take advantage of, is we now have our antiderivative. So what's going to happen on this integral is we're going to have the antiderivative is, I need to write the right thing, the antiderivative is this thing right here. So I'm going to write that as negative 1/2 cosine of 2x plus cosine x, and I'm going to be integrating that or evaluating that from 0 to pi over 3. Okay, now I'm going to erase all this stuff here, so I've got the antiderivative, and I'll kind of talk about what you could do to finish up the problem then, so I have enough room to go through this. Okay, now what you're going to find on this is if you did this integral right here, the antiderivative is just going to be this in reverse. Okay, so what you would end up having is instead of this, you would have 1/2 cosine of 2x minus cosine x, and you would be evaluating that from pi over 3 to pi. Okay, now let me show you why that's the case. So if you were doing this integral right here, if you were doing the integral of sine x minus sine 2x dx, I could actually rewrite this as the sine of negative sine 2x minus sine x dx, because it's the same thing. Okay, and see, we already did that antiderivative, and we got this, but again, that negative comes out in front. So what you're doing is you're doing this integral that we've already done. Okay, so when you see this situation, in this case, then basically those antiderivatives are just going to change the signs. So that's something you can take advantage of on this problem. Okay, now what I'm going to do is I'm going to evaluate these two definite integrals then. Okay, and just kind of do this at the side. So let's work with the area of region 1. Let's go ahead and evaluate this integral. So what we're going to have is negative 1/2 cosine of 2 times x, the upper limit, pi over 3, plus the cosine of the upper limit, pi over 3, minus, and then do the same thing with the lower limit, 0. So that's going to be negative 1/2 cosine 2 times 0 plus cosine of 0. So we need to evaluate those things then. Okay. All right, I'm going to magically make a unit circle appear. Okay. So that we can get this kind of, so you can refer to this. All right. So what we're going to have is, this is going to really be negative 1/2 cosine of 2 pi over 3 plus cosine of pi over 3 here. And then we're going to say minus negative 1/2 cosine of 0 plus cosine of 0, and then we're going to work this out and evaluate this. All right, well, let's see. The cosine of 2 pi over 3 is going to be negative 1/2. So I'm going to write this as negative 1/2 times negative 1/2 plus the cosine of pi over 3 is going to be 1/2. So that'll take care of that. Then we have negative 1/2 cosine of 0. Cosine of 0 is 1. And then cosine of 0 again is 1, like that. So that will be the arithmetic that we do. Okay. All right, so I'm going to cut out the unit circle. And then we're going to go ahead and work this out. Okay, working the arithmetic out. So this is going to be, it looks like 1/4 plus a half minus negative 1/2 plus 1. So we want to go ahead and get all that worked out. Okay, so I'm going to do this. I'm just going to have 1/4 plus a half minus 1. Okay, just distributing the negative through the parentheses. Okay, so let's see. We have a half and a half as a whole. So it looks like we have 1/4 plus 1 minus 1. Those cancel out, so it looks like that area is going to be 1/4. So when I go down to kind of polish up my answer, so we know that the value of region 1 is going to be 1/4. Okay, so we've got that taken care of now. Okay, so now what I'm going to do is I'm going to focus just primarily on the second integral now. So we're going to do the area of region 2. So we are actually looking at this second indefinite integral right here. So we're going to do 1/2 cosine of 2 times pi, minus, and this is going to be cosine of pi. So again, I'm just plugging in that upper limit. And then minus, now evaluate the lower limit, so we're going to have 1/2 cosine of 2 times pi over 3 minus cosine of pi over 3, and then we're going to evaluate that. So what I've done essentially is plugged in the pi, so you can see that I've done that, and then plugged in the pi over 3, so you can see that I've done that. Okay, now I need to work this out, so this is going to be 1/2 cosine 2 pi minus cosine pi minus, and then this is going to be 1/2 cosine of 2 pi over 3 minus cosine of pi over 3. Okay, then you can look at a unit circle to get that worked out. So let me move this up just a little bit and insert my magic unit circle. Okay, so what I have on this is the cosine of 2 pi is going to be 1. So I'm going to write this next step as 1/2 times 1 minus the cosine of pi. The cosine of pi is negative 1. Then move over to the next part. We have 1/2, and now we have cosine of 2 pi over 3. Cosine of 2 pi over 3 is negative 1/2. So I'll put that in. And then minus the cosine of pi over 3, which is 1/2. So I've got minus 1/2, and then let's go through and let's work out the details of that. Okay, just kind of double checking. Cosine 2 pi is right. Cosine of pi is negative 1. Cosine 2 pi over 3 is negative 1/2. Cosine of pi over 3 is negative 1/2. So you got to kind of take your time on these problems and double check things so that you're not making any mistakes. Okay, because it's easy to make them. Okay, so this is going to give 1/2 plus 1 minus negative 1/4 minus a half. So that's going to be 1/2 plus 1 plus 1/4 plus 1/2. Okay, when you distribute the negative, a half plus a half is 1. So that's going to be 1 plus 1 plus a fourth. So this looks like this is going to be 2 1/4, or that's equal to 9/4. 2 times 4 is 8, plus 1 is 9. Okay, so it looks like we have our two regions now. So we have that integral was 1/4, that integral was 9/4. So now we're ready to add these two things together. Okay, all right, so now let me just kind of scroll up here and show you what I got. So we now have this second region calculates as 9/4. So now we're ready to add this together to get 10/4, and then that reduces to 5/2. So it looks like the grand answer to this problem after all that work is 5/2, okay, 2.5. All right, so that should be the final answer of that problem. Okay, and that could be checked with technology as well. Okay, so I'm going to go ahead and just do a real quick area of region 1 check. Okay, let's check this integral right here and just make sure that we got this one right. So you just put in your calculator, you just put in sine 2x minus sine x. You want to be sure that you're in radian mode. Window is 0 to pi over 2, but make it a little bigger. You can even, pi over 2 is 1.5, I think. So let's just use a window like this. Okay, and then see what we get. And remember, we're graphing this. We're not graphing the original problem. We're checking the integral. Okay, so we're integrating from 0 to pi over 3. So I can go trace option 7. Lower limit is 0. Upper limit is pi over 3. And it'll shade it in, and it should give 1/4. We ended up getting this area of 1/4 here. So 0.25 and 1/4 are the same thing. All right, so that verifies that. Now let's do the second one. The second integral was doing this backwards. We had sine of x minus sine of 2x. And let's take that out a little bigger. We need to take that out a little bigger than pi. So see, pi is 3.14, so I'm just going to put 4 in. And who cares what the scale is, really? That makes absolutely no difference. All you're doing is using technology to check the integral. It doesn't matter that you can't see the y value on that. That isn't going to make any difference, although you could expand that thing out a little bit too if you wanted to. So let's expand that maybe to 2 for a y max. And then we'll check our integral on our calculator. So we're integrating from pi over 3 to pi. So let's go second trace, option 7. Lower limit is going to be pi over 3. Upper limit is going to be pi. It'll shade, and let's see, we got 9/4 on that. 9/4 is 2.25, so it's the same thing. So 9/4 is the same thing. Right, so that means we have verified that we have the right answer to the problem. Okay? All right, hardest part of that problem to me is all this arithmetic right here. So that's the biggest work of that problem. Okay, very good. So next thing I'm going to do is we're going to move on to one last example. And we're going to do this integral. And I'm going to go ahead and run through the entire area on this one. Okay, now if you look at this region right here, this one is set up so that what we want to do is integrate with respect to y. Okay, well, I'm going to go ahead and close off this video, and then I'm going to do the last 3 examples in a different video because they're all with respect to y.